Alright, hi everyone. We're going to move on to a new chapter. The chapter is about inverse functions, and the first section is called inverse functions. So you probably definitely have heard of inverse functions before, but so far in calculus we've only talked about, a very small set of functions. We've talked about maybe polynomials like this thing. Talked about maybe like square root functions, like functions that have a square root or a cube root. And then we've talked about trigonometric functions. So examples are things like this, which is like a pretty relatively small class of functions. So we want to kind of expand the set of functions that we deal with and know how to do calculus with is the idea. And to do this, we need to talk about the inverse functions, because when we talk about the inverse of functions, then we can, open up a new set of class of functions. So like, the inverse of sine, which you've learned this in trigonometry, is the inverse sine function. So for example, we can ask, what is the derivative of sine inverse? What is the integral of sine inverse? Questions like this we want to try and answer. And we haven't talked about this yet, but you've seen this in other classes like the log function or the natural log, ln of x. So the inverse of ln of x, the natural log function, is the exponential function e to the x. And some would argue that this function is, in some sense, and I would agree, the most important function in all of mathematics, or at least many branches of mathematics. And so, we'd like to know what the derivative and integral of this is, what the derivative and integral of this is, and things like that. So to do this, we need to first just talk about what inverse functions are in general, and then we can kind of move on from there. Okay. So to do that, remember, what is a function? Well, it takes in an input and then it gives you an output. And normally we deal with like functions where you stick a number in and then you get a number out. But let's do something kind of different. Let's say we have a function L of x takes in an animal. So x represents some animal, and it gives you how many legs it has. Okay. So now this function, its input is an animal, its output is a number, how many legs it has. And normally, the domain and range of the function, they're like sets of real numbers, but more abstractly in this setting, you could just think of them, a lot of people think of them as just blobs. So people call these things sets. So the domain here is the collection of inputs, and then the range is the corresponding set of outputs. So for example, one thing in the domain, here we can list every single animal that we'd like, but for now let's just start small. Let's just say we do dog. So see, this is an input, so it goes in the domain. Okay, and then normally you draw an arrow from the input to its corresponding output. So what would L of dog be? So if you stick dog into the function L, this tells you how many legs it has. This should be 4. So we're going to associate dog with the number 4. Okay. So we're going to draw an arrow from dog to 4. And then we can kind of do this. Let's do something similar. Let's do, I don't know, let's kind of do a trick question. Fish. How many legs does a fish have? Well, it has 0. So we can associate fish to the number 0. So we draw an arrow to it. And then maybe let's do one more thing. Let's see. I guess we can put human on here. We're technically animals. So human, we got 2 legs. So we'll get associated to 2. So we draw an arrow from human to 2. Now, there's another way of representing this, which we know is with ordered pairs, right? So another way of representing this is the ordered pair is the first coordinate is the input, and the second coordinate is its corresponding output. So we would get a set of 3 ordered pairs here. We would get dog, comma 4, fish, comma 0, and human, comma 2. And so on and so on. Okay, so this is like one way of representing it with the arrows and blobs. This is another way of representing it. Okay. So what the inverse function does is it does the exact opposite. It takes something from the range as the input, and then it tells you what it corresponded to in the domain. So you kind of just run the arrow backward. So the first observation is, this is running out of room, is I'll just write it here, the domain of, and when we write the inverse function, so the original function was L, right? We wrote capital L. But in general, we just think of it as f. You know, we write f for an arbitrary function. We write it as f with a -1 here. This does not mean the reciprocal of f. So it does not mean this is not equal to 1 over f. So the inverse function is not 1 over f. An example of this is, you know, sine inverse of x is not 1 over sine x, because we know what 1 over sine x is. It's cosecant x. So had this been equal to cosecant x, there would be no need to create this new function sine inverse. So it's not the inverse. It's not like 1 over that thing. This is just the notation. So the domain of f inverse, this is the notation for the inverse function, is the range of f and the range of f inverse. So the domain was the range of the original function, and the range of this guy is going to be the domain. Okay, so this is kind of a mouthful, and I had to stop there and make sure I'm writing it right, because it's a little bit of a mental gymnastics. But this is one thing that we're going to notice. So you flip-flop the domain and range. The original function takes something from, you know, the collection of animals that we're considering, and it gives you a number, the number of legs. But the inverse function is going to do the opposite. It's going to take something, the input, aka the domain, will be a number, the number of legs, and then it'll tell you which animal has that many legs. It does the opposite. So if I say 4 legs, you know that that's going to be associated to a dog. 0 legs, that's associated with a fish, and so on. So that's one thing about the inverse function. And because of this, the ordered pairs for the inverse function are just you flip the order of these. So this is f. This corresponds to the original function L. Now, if we flip all the ordered pairs, this is going to be the correspondence for L inverse. So now I stick 4 into L inverse, and I get dog out. So this is the input, that's the output. So L inverse is how we're going to write it. We say L inverse, but it's L raised to the negative 1 power is how we write it. So what this means, for example, like here, this top line tells you that L of fish is 0. And then similarly, we know that L inverse, so this is a function, you stick 0 into it, that's its input. Remember, the first input is the first slot in an ordered pair is the input. We know that L inverse of 0 is fish. See, it's the exact opposite. So the arrows in blue correspond to F. But now if I draw this back, drawing this backwards, so 4 goes to dog, 2 goes to human, and 0 goes to fish. That relationship is given by, or L inverse, sorry. We call this L. So now you go from this guy to that. So notice the domain and range have interchanged. Now the domain of L inverse was the range of L. And the range of L inverse, the set of outputs, was the original domain of L. So they flip-flop. Okay, so the inverse function kind of lets you, in a sense, recover information. If you went from one set of things, if you went from this set to the other, this lets you go back to the previous set. Okay? Now, there's another thing that you may have noticed. What this is this very important property. What happens if I take, for example, L of human? Okay, that's going to be equal to 2. Now, let me stick this into L inverse, right? Because this is an input. This is a number in the range of L, so it's going to be in the domain of L inverse. So then if I take L inverse of 2, which is allowed, I get human back. Which makes sense, right? We had human here, and then it was associated to 2. If you use L, it takes you to 2. And then if you apply L inverse, it takes you back to human. So notice it gets you where you started. Okay? And then if we write this all in one go, a faster way of writing all of this would be L inverse of L of human. Remember, this is using function composition. Because first we calculate what L of human is, which is 2. And then that's just human. Okay? So this is kind of interesting. And of course, this is going to work with numbers too, right? If we're not using abstract things like a human or cat or whatever, this is going to work just the same with numbers. So this is an interesting observation. And it leads us to this thing that we just noticed. Is in general, if you let x be any input here, you've noticed, and then if we go back to f, if you take f inverse of f of x, you just get x back. So this is really important. Now, what if you do the opposite process? What if instead you start with something here. So first you take L inverse. So first you take L inverse right there. So L inverse of 2 gets you to human. And then you apply L to get you back to 2. Well, the same thing happened. The number you started with, or the thing you started with, you ended up just going back to it. So if we summarize this in the way that we did here, what we were doing is we took L inverse of 2, step 1, and that gave human. And then we could stick this number into the original function L, and that gives 2 back. And similarly to what we did, that means that now if we take L of L inverse of human, or sorry, 2 here, we get 2 right back. So then we can summarize that. Because notice this is like F, that's F inverse. F of F inverse of X is also X. You have to be really careful though with this thing. This is, I believe the book calls this the cancellation property. Oh, the cancellation equations. But you have to be careful what X is representing. Notice X in here, this was from the domain. It was like human. It was an animal. So this X here is from the domain of F. This X from domain of the original function. It was from the domain of L, like in our case. But this guy, like 2 here, it was from the range of L. So this X here is from the range of F. So it's really important to keep in track where this X is coming from. But this is a really interesting property of the inverse function, but it makes sense, right? It completely makes sense. And it's kind of the goal of the inverse function. If the inverse function didn't allow you to go back from the range to the domain, it would kind of not be called the inverse function. Okay? And we're going to use this property to find a very interesting calculus result in a second. Okay? But now we kind of have to talk about a somewhat technical issue. And so what do I mean by technical? By technical, I mean it involves some theoretical concepts in math. This is kind of the idea here. So this depends on the domain. So on a particular domain, the function f may not have an inverse. So let's see why. So the original definition of a function that you learn, whenever you start talking about them, is every input just gives you one output. So if you tell me f of 2 is either 7 or pi, that's not good. Because I'm going to be like, I need it to be one particular number. Either it should always be 7 or it should be pi. The output, so if you stick 2 into your function and it's sometimes 7 and sometimes pi, that's not good. Because I don't know what it is. I need it to be one clear thing. And with inverse functions, this problem can happen very badly. This very particular thing can happen. So let's go back to the first example we were talking about. Is notice the domain that we originally started with was fish, human, and dog, right? Let's see if the inverse function makes sense in this case. No. And then this was 0, 2, 4. Okay. So L took us here. So now, if we kind of think about this in words, what is this saying? It says, if I ask, how many legs does a fish have? The function will tell you 0. How many legs does a human have? The function would tell you 2. Now the inverse function kind of would do the opposite, right? If I say, what animal has 0 legs? You would say, fish, according to this. So it's clear that this thing would go back to fish. So L inverse is in red. So you would say that L inverse of 0 goes to fish, because I asked, what animal has 0 legs? And the answer to that is fish. Now, you may already be thinking, well, okay, but is that the only animal with like 0 legs or something like that? I guess fish is a very general, broad definition, so it could include like a shark, whale, or whatever. But let's think about, once we get to dog, this will be very clear. So if we take L inverse of 2, we get to human. So I say, what animal has 2 legs? You say human. But now you say, what animal has 4 legs? In the context of this function, you would say dog, but I can think of a lot of other animals that have 4 legs. Like a cat, that also has 4 legs. Or like a pig. So here, because of the domain that we've picked, we don't run into that issue. The answer is clear. Because the domain that we picked only has these 3 options, our answer always has a clear value. If I ask, of these 3 things, which animal has 0 legs, it's clear it's a fish. Which one has 2? Human. Which one has 4? A dog. But now, if I pick a bigger domain, and see, this is where a certain domain comes in. Now if I include cat here, this is very bad, because now cat would also go to 4. And now it's unclear what the answer to the inverse question is. Now if I say, which animal on this list has 4 legs, you'd be like, well, it could be dog or cat. And then it's not clear. Then L inverse of 4 could be dog or cat, which is not good. Remember, if this thing needs to be a function, it needs to have one clear output. But now the input of 4 has 2 outputs, and that's not good. So this is not a function. L inverse would not be a function. And so that's why the domain, it's important to have a very particular domain. Okay, and now let's see how this corresponds to, like, there's a very clear way of knowing whether a function will have an inverse or not. There's a very nice way of knowing that. And you can kind of see it. Is notice that these two numbers both went to 4. And that's what caused the problem. Because now, when you do the inverse problem, L inverse of 4 has two outputs. It has two different outputs. So we don't want this to happen. We don't want to have two numbers, or inputs, but we're going to go back to caring about numbers only. We don't want two numbers or inputs to have the same output. And when that does not happen, when always distinct numbers have distinct outputs, you call the function one-to-one. So to summarize this, to give a summary of what we just found, is a function on a domain D one-to-one. This is so if your function, the original function f, so if the original function is one-to-one, then it will have an inverse on this domain, whatever the domain is. And let's define what one-to-one is. Sometimes also just written like one-to-one with numbers. Okay, so this is kind of like this is like the idea. This is not the actual definition of it. We'll talk about the actual definition for a second. So it's one-to-one if once it hits a certain output, it never gets to that output again. Because if it does, then we have that problem. Like we saw when dog hit 4, that was good. But then when cat also hit 4, not good. So a function is one-to-one if it never repeats an output. But formally, the way of writing this is this. Formally, one-to-one if okay. So this seems really weird at first, and for the most part, we won't deal with this very formal way of doing it. We're going to come up with a graphical way of figuring out whether a function is one-to-one or not in a second. But what this is saying is that if these numbers x1 and x2 gave the same output, they have to be the same. So then they're not distinct. So like essentially it would say like cat and dog are the same thing. If cat and dog were the same, then they would just collapse to one thing, and then that one unique thing goes to 4. Is kind of what it's saying. But this is a little clunky in the context of this class to deal with. So what we are actually going to do is use this thing called the horizontal line test. It's a graphical way of determining whether a function is one-to-one or not. Or the HLT. So if a function is one to one, if it passes the horizontal line test. So if you do the horizontal line test and then it works, that means that function is 1 to 1. If it doesn't work, it is not 1 to 1. And what does passing the horizontal line test mean? It's the same thing as passing the vertical line test. So let's think about sine x on 0 to 2 pi. So here's pi, here's 2 pi. If I draw a horizontal line, and you know, this has to be every single horizontal line possible. If it fails for just one horizontal line, it fails the whole test. So just because it works for some points doesn't mean it's foolproof. If it fails for just one point, then it's over. So if we can just find one horizontal line that touches the function twice, which it does, this thing fails the horizontal line test. So on this domain, on the domain 0 to 2 pi, sine x is not 1 to 1. But you're probably thinking, hey, didn't you say there's an inverse sine function? And yes, and the key thing is, remember, all of this depends on the domain, the particular domain. So if you remember this way back when from trig, is if you consider sine x on this domain instead, negative pi over 2 to pi over 2, it is 1 to 1 there. And this is the domain that we consider it for the inverse function. So it hits negative 1 at negative pi over 2, and it hits positive 1 at pi over 2. So it looks like this. And notice this will pass the horizontal line test. If I draw any horizontal line, it never touches the function in more than one spot. So this does pass the horizontal line test. So this all is dependent on the domain that you're considering. So keep that in mind. This is very important, that on a particular domain it may not be 1 to 1, but if you shrink it a little bit or modify it a little bit, it could be 1 to 1. Okay, and so this is the key thing that we need to first check to know if it has an inverse or not. Okay, so 1 to 1 is the property that tells us this, and the horizontal line test allows us to do this. Okay. So maybe let's do an example. Not an example, sorry. Moving on to another new concept. Okay, so now if in some cases we can actually find an explicit formula for the inverse function. So this is the idea. So suppose y equals f of x. So you know what f of x is. For example, like y equals x squared plus 1. That's f of x. And f is 1 to 1 on some domain. Okay, so we know that on this domain the inverse function exists. Okay, so yeah, step 1 is we're gonna write y equals f of x. So like y equals x squared plus 1. You just expand this out. Then what you want to do is solve for x. So you want to form an equation in the form x equals. Solve for x. This may or may not always be possible, but if it is possible, you want to do this. So then you'd get something in the form x equals, and then last but not least, you would switch x and y. So you'd switch back at the end. So you have, instead of now y equals f of x, y equals some other function, and that's the inverse function. So let's do an example because this may seem really weird. Okay. Okay, so suppose we have y equals x cubed plus 2. Okay, so this is our function, y equals some f of x. So step 1, we switch the x's and the y's. So this is now x equals y cubed plus 2. So everywhere I saw y, which is just going to be one place, you replace that with an x, and had there been more terms with x's here, you would replace them with a y. So the only one was this, so that became y cubed plus 2. Now, you want to solve for y. So you want this thing to be in the form, you do not switch it. I'm getting ahead of myself. You switch it at the end, sorry. Step 1 is you just solve for x. So if we have y equals x cubed plus 2, you would subtract the 2, and then you would take the cube root of both sides. Okay, so see, now we have something in the form x equals. Okay, so we did this. Then step 2 tells us to now, I jumped the gun, is to now replace the x's with the y's. So when you do that, you get the cube root of x minus 2 is equal to y. And then step 3 just says, okay, now this is some function of x, right? If I hand you this thing x, you can tell me what y is, so it works like a regular function, but this is now an inverse function. Because notice, where is this x coming from? This x, remember, if you're sticking it into the inverse function, this x here is coming from the range of the original function. So that's what it means by x. Remember we did this earlier? You have to be really careful what x means. So we know that y, which is f inverse of x, is this guy. So this is the formula for the inverse function. But this x comes from the range of f of x, the original function. So remember, the input of the inverse function, it comes from the output of the original function. This x here for the original is just from the regular domain. This is from the range. So you have to be very careful. So yeah, this thing here though would be f inverse of x. So this is an explicit formula for the inverse function. You know, if you do have a function, if it is a function, it'd be nice if you can find an explicit expression for it. Okay, and then now what we want to do is, up to this point, we haven't done any calculus, right? And this is apparently a calculus class, so we need to start to talk about the calculus of inverse functions. It's a good start. But one little thing that might come in handy, another thing that kind of helps us know if a function is one-to-one, aka has an inverse, is this. I guess we can call it a theorem. If so if it's always increasing or always decreasing, so if the function always is going up or always is going down, on a domain it has to be one-to-one. And this makes a lot of sense if you think about, for the function to not be one-to-one, let's say it starts going up and then it dips back down. See, now this, if I draw the horizontal line now, that's going to create a problem. Anytime it goes up and then dips back down, it has the chance of hitting a number that it already hit before, so it would fail to be one-to-one. But if the function is always increasing or decreasing, this thing will never happen. So either if the function is always increasing, and by increasing I mean like strictly increasing, meaning it always goes up. Some definition of increasing say that if the function stays constant, if it doesn't change, it's called increasing but not strictly increasing, but this would fail the horizontal line test. So by here I mean it is always going up. It never stays constant. If it's always increasing or always decreasing, it doesn't have the chance to come back down or come back up and fail the horizontal line test. So, see, it won't fail the horizontal line test. So that's something really nice. And not too shabby, as you may ask, like, well, how do you know if the function is increasing or decreasing? Remember from calculus 1, you can do this by finding the derivative and checking whether it's positive or negative. If the derivative is positive, then it's increasing. If the derivative is negative, then it's decreasing. So there is a nice way to do this with calculus as well. So this is a really nice theorem. Okay, and so now here's another theorem that kind of just tells you some properties about an inverse function. So if f is continuous on AB, so if the function is continuous and one-to-one, so this here guarantees that the inverse exists. Then f inverse of x exists, and so if the original function is continuous, then its inverse will also be continuous as well. Like if the original function doesn't have any breaks or holes in it, the inverse should also be like that, is essentially what it's saying, which again goes well with our intuition. And then the next thing is this, is what is the derivative of an inverse function? So say you want to know f inverse of x prime. So you want to know the derivative of this guy, which may be a better notation for this. F inverse prime of x. So keep in mind that prime there, the notation gets kind of heavy. So this is, maybe a parentheses here goes nicely too. So yeah, the book puts a parentheses here just for extra precaution. So this is the function, its derivative, prime denotes its derivative, and it's at the point x. So derivative of inverse function at x. So, you know, f inverse is a function. It does have a graph. So it's just saying what is the slope of the tangent line at the point x. You know, one very famous set of functions, an inverse function, is if you think about f of x equals x squared on this interval, 0 to infinity, then the function, you know, normally it's a parabola. If you include negative numbers, it won't be 1 to 1 because it would fail the horizontal line test. But if you only allow positive numbers, so you're just looking at this branch, then yes, it is 1 to 1. And the inverse function of this is the square root function. So f inverse here is root x. And then think about the cancellation properties. What happens if you take f of 2, that's going to be 2 squared, that's 4. And now take f inverse of 4, which is the square root of 4, and that gives 2. So, you know, they're canceling each other out. It makes sense, right? If you take a number, 2, and you square it, you get 4. Then if you take the square root of that, then you get 2 back. So you get 2 out of this. So this is like the cancellation property. And so we know what the graph of these functions look like. So, okay, sorry about that. Camera cut out again. So what we were looking at was we wanted to take now the derivative of the inverse function at some point x. But we kind of need to give a meaning of what x is, because remember, the inverse function, the domain of it, its inputs, is actually the range of the original function. So here was an example of a function and its inverse. So like we were saying, if you take x squared on 0 to infinity, then it's 1 to 1, and its inverse is actually the square root function. Which, if you think about that for like a few seconds, it makes sense, because they have to undo each other, right? So now what happens when we graph these guys? So let's graph these, both of these on the same plot. So, you know, if you stick 0 into this, you get 0. And then if you stick, well, you maybe put these with, let me try and space these out properly. Okay, so if you stick 0 into this guy, you get 0. And then if you stick 1 into it, you get 1. And then if you stick 2 into it, you get 4. You know, so we get the very, you know, famous parabola. And then what happens when you stick, you know, 0 in here, you get 0 again. So that's the same point. And then if you stick 1 in here, you get 1. So they intersect at this point. And then all the way until if you stick 4 in here, so the input is 4, the output is 2. So Square root kind of looks like this. Now, the question may be, which one is on top of the other? So let's take a number. Obviously, the parabola ends up winning, and they intersected these 2 points. So between those, which one wins? Well, let's take like 1/2. That's a number in the intermediate. If you take, 1/4. If you take 1/4 and you square it, you get 1/16. But if you take the square root of 1/4, you get 1/2. So this number is bigger than that one. So the square root on 0 to 1 is actually bigger than the parabola. So it looks something like this. It's bigger, and then it tapers off and the other one wins. So this is f inverse, which is the square root function. Okay? And so the idea is, can we find the derivative of this guy? Now you may say, of course, well, once you know the formula, you know if it's root x, then yeah, you can just use the power rule and whatnot. But the idea is there a way of relating this to the original function's derivative of f? And the answer is yes. And it turns out to be this. Turns out to be 1 over this guy. So f inverse of this number x, that gives you another number, and you stick that into the original derivative. So in a sense, what this is saying is the derivative of the inverse function is just the reciprocal of the derivative of the original function. So maybe let me write that out. And we'll do an example. We'll see what it kind of means in this context here. So what this means is, so this is a really important formula. We'll star that. What this means is that so the derivative of f inverse is the reciprocal of the original function, and vice versa. So they, in terms of derivatives, they are actually the reciprocals of each other. And let's see an example of this. So notice that the point here on the parabola, or over here, sorry, this ordered pair here is 4, 2. And then this ordered pair here is 2, 4. Which, remember, this happens, right? In the original function, whatever your ordered pair is, the inverse function flips it. We already talked about this, so you flip the ordered pairs, basically. So then, if you want, for example, to know the derivative of the square root function at the point 4, for example. So say you want to get that derivative. And I believe this is an example in the book. Yes, it's example 6 from the book. And they do another point. They do 1, 1. They do the intersection point. We can do both just for clarity. But at this point, they intersect. So here, when you flip-flop the ordered pair, the order doesn't matter. So yeah, say you want, and here by f inverse, again, we mean, in this case, we mean root x. Say you want f inverse, so you want the derivative at 1 here. So at the point 1. So according to this formula, this is 1 over f prime of f inverse of 1. So you just replace everything, every x, with what it needs to be. Okay? Now the question is, what is f inverse of 1? Well, because these ordered pairs are the same, remember that flip-flopping them doesn't matter. So it's the same thing, meaning that f of 1 is equal to 1, remember, if we had this relationship that f of a was equal to b, for example, then you knew that f inverse of b was equal to a. This is basically the relationship that the inverse function gives you. And a way that you can actually derive this is with the cancellation properties. Because if you take the inverse of both sides, if you take f inverse now of f of a, that is equal to f inverse of b. And then what do we say happens here? Anytime you have f inverse and then f, this thing just comes out. So you get basically a equals f inverse of b, which is what we have here. So it's kind of like, in a sense, the cancellation property is what's causing that. And this is why the ordered pairs flip, right? Because the ordered pair, the input here is a, the output is b. In this case, the input is b and the output is a. So this is what flip-flops them. But in this case, they're the same, so it doesn't matter. Okay, just maybe let this sink in for a second. Okay, yes. So, long story short, is that f inverse of 1 is equal to 1. So this whole thing is 1. So we just get 1 over f prime of 1. Okay, well, what is the original function? F of x is x squared. Meaning, what is f prime? It's 2x. So this is just 1 over, when you stick 1 into this function, because that's f prime of 1, is 1 over 2 times 1, which is 1/2. Okay? And then again, we can actually calculate the derivative of this function explicitly. The derivative of that is of root x is 1 over 2 root x. So notice when you stick 1 in here, you also get 1/2. So that's just a nice thing. Now, maybe let's do a more interesting example. Is say you want let's see. Now we can stick with this guy. Say you want f inverse prime at 4 now instead. So this would be 1 over this guy. Okay. Now looking at this, what is f inverse of 4? So you stick 4 into this function, it tells you the output is 2. So this is just 1 over f prime of 2. Because, if you look here, f inverse of 4 is 2. And that is because, you know, this goes both ways. Because f inverse of 4 is 2, f of 2 is 4, and vice versa. Again, you can get these from the cancellation properties. And we know this, right? Because if you stick 2 into x squared, 2 squared is 4, and vice versa. So, okay, so now that we have this established, again, we just say this is 1 over f prime of 2. Well, we know what f prime is. It's 2x. So this is just 1 over 2 times 2, which is 1/4. Which again, we explicitly know the derivative of this function. It's 1 over 2 root x. So this is literally what f inverse prime of x would be. So if you stick 4 into this, this will be 1 over 2 root 4. That's f inverse prime of 4. And then, right, this is 2 times 2 once the square root is gone, so that's 1/4. So again, we can confirm this just by what we know. Okay, so that's really interesting. And remember that what the derivative is telling you is the slope of the tangent line. So when we were calculating this thing at 1, when we erased it, we were looking for the slope of the tangent line on the red curve at x equals 1, so the slope of this line. And then when we did it at 4, we were looking at the slope of the tangent line at 4, and so on. So again, it still has the same interpretation as the regular derivative. It's just establishing this really interesting relationship. It's saying that, it's just the reciprocal of the original functions, which maybe is the reason why this notation was born, because this does relate in a reciprocal way. The derivative does, not the original functions. So that's kind of interesting. And then last example, so this again from the book, it says, suppose this is your function. So you have 2x plus cosine x, and you want f inverse prime at 1. Now in this case, it's a lot harder to find the explicit formula for the inverse function. So we can't do that. Like with the square root, you can find it super quickly. Remember the process we did is if you have y equals x squared, what do? We solve for x, so you take the square root, and then you flip x and y. So you got that root x was equal to y, and this was the inverse function. So that was super quick to do. If you try this here, you write this now as y equals 2x plus cosine x, it's kind of hard to explicitly solve for x, because in the other case we had y equals x squared, you just took the square root and you got root y equals x. Here this x is trapped inside of cosine, so it makes this very tricky. So in this case we don't have the ability to just find the inverse function so easily, at least with that method that we developed. So this is where this formula comes into play. So according to the formula, this is just 1 over f prime. We can calculate f prime. We know what f is, so we can take its derivative. It's f prime of f inverse of 1. Okay? Now the question is, what is f inverse of 1? So f inverse of 1 equals question mark, which maybe we can call it x, right? Because it is some input, right? This is a number from the range, because what you stick into the inverse function is from the range, and what it spits out is something from the domain of the original function. So it's like an x. And again, if you apply like the cancellation property, what this is telling you is that if you take f of both sides, then this cancels out. This means that this number x should be a very particular number. It should be the number that when we stick it into this function, it gives us 1. That's what we want out of this. Now, if you think about it, what happens when you stick 0 into the function, into the original function? So if you stick 0 into it, what do you get? You get 2 times 0 plus cosine of 0. That's just 0. This is 1. And look, lo and behold, we get 1. So the number x that we were looking for is actually 0. So x is 0 actually in this case. So we found what f inverse of 1 is. It's 0. Meaning that this becomes 1 over just f prime. Now this whole thing is 0. Well, it's f prime of 0. Okay? So to finish this out, we need to find the derivative of this function. And then that's not too bad, because we took calc 1, we know how to do this. F prime of x, as you take the derivative of each of these, this one is 2, and then this one is minus sine x. So then what is f prime of 0? It's just 2 minus the sine of 0, which this thing is 0, right? The sine of 0 is 0, so this is just 2. So this gives 1 over 2, and that's the final answer. So without having the explicit formula for the inverse function, we don't know what f inverse is. F inverse of x, I have no idea what that is. But this formula is really nice. It tells you that you can still tell me what the derivative is at any point. So if you'd like to know the slope of the tangent line of this function, even though you don't know what it is, you can still find it. It's just the reciprocal of the original functions. Okay? Now, there's one small, minute detail that we have to think about, is how do we know the inverse function of this thing exists? Well, it goes back to the fact that this function is always increasing. So notice we took the derivative, right? F prime of x, that was just 2 minus sine of x. Because this number sine x can never be larger than 1, the biggest thing that this can be is 1, that means that the smallest output that the derivative can take on is 1, right? Because in the worst case scenario, it's 2 minus 1, which is 1. But every other time, this number is smaller than 1. In fact, the smallest it gets is negative 1, so 2 minus negative 1 is actually 3. So this function takes on values between 1 and 3. But that is always positive, right? And notice we just established that the first derivative is always positive. This means that the original function is increasing. And because it's increasing, we know it's 1 to 1, right? It will easily pass the vertical line test. If a function's always increasing, the horizontal line test, then no matter any horizontal line you draw, it will only touch the function at one point. And it's because it can't loop back down. Because it's always increasing, it doesn't loop back down and then fail it. So that was a small theoretical reason why we knew that it did have an inverse. Okay, awesome. So this is a good stopping point. See you guys next time.